Using a differential energy balance, we can actually derive a heat diffusion equation for cylindrical coordinates. It's a very similar process to how you would derive a 3D heat diffusion equation. In fact, many of the same principles we use for both of these are the same. The first concept that you want to understand is, of course, conservation of energy, which is the equation in energy in minus energy out plus the energy generated is equivalent to the energy accumulated. And this concept is going to be used to create our final equation. Let's start by visualizing a cylindrical object so we can understand how we can find the elements that are going to be used for this equation. So we have a cylinder here, and we're trying to find how the heat flows through it. We have our z direction, our heat flowing through our cylinder. And then if we take a closer look, we'll also have the radius of our cylinder as another dimension. Let's draw this more visually appealing. So our radius is another dimension. The third and final dimension, if we were to say take a cross-sectional area of the cylinder, is theta. That's going to be our third and final dimension. So one huge, very important part of solving for this equation is knowing what the volume is for your cylinder. Why is that important? Well, you're trying to find the energy within the cylinder, which means you need to have the volume in order to determine how the energy is within that volume. So for your volume, let's say you have a cross-sectional area of the cylinder, and let's draw that out. You're going to have your radius, right? This is your radius right here. And you're going to have your theta. But this is going to be your radius r, and this is going to be your change in your radius, because you're increasing your radius or decreasing it depending on what the coordinates are. And right here is going to be your theta and your change in theta. Now for your z direction, let's visualize this in a more 3D manner. Right here is going to be your z direction and your change in z. So our volume is going to be equivalent to our radius multiplied by our change in theta, our change in our radius, and our change in our z direction. And that's very important. We can use that volume and apply it to our heat diffusion equation that we similarly used in this situation, but we have to consider that there's another element in there. This radius right here we did not have when solving for this 3D heat diffusion equation. But let's look at what we have here. So we have our energy accumulated and our energy generated, and those two equations are essentially going to be the exact same, but we're going to add in that radius to the volume right here. So let's take those two equations. We have our energy accumulated, and that's going to be equivalent to our density multiplied by our heat capacity and our temperature over our time multiplied by our radius, our change in theta, change in our radius, and our change in our z direction. Our energy generated is going to be our heat flow multiplied by that volume, which is our radius, our change in theta, our change in radius, and change in z direction. Now for our energy going in and out, again, we're going to use the same concept as in our 3D heat diffusion, just taking into consideration that our volume is going to be a little different. And we're going to use that Taylor series expansion that we briefly talked about. So this is the equation, this is the general format of the equation that we want to use, which we have that our heat flow at the change in our x direction, or whatever direction you're going, so this could be for the radius, for the theta direction, for the z direction, is relatively equivalent to our heat flow in our original direction x, plus the change in the heat flow over the change in the x direction at the change in the x direction when it equals x, where the change in our x direction minus x. So let's take that equation, let's apply it. So we have for all net heat flows, and our net heat flow is equivalent to as you see here, our net heat flow is equivalent to our heat flow at a certain direction. Let's just assume that we're going to start with the z direction. So our heat flow at the z direction minus our heat flow at the change in the z direction, that's going to be our net heat flow, which is our energy flowing in and out. That's going to be our net heat flow. So since we know that our heat flow in the dz direction is equivalent to this equation right here, we can substitute that in and find that our net heat flow in the z direction is equivalent to our heat flow of our z minus heat flow of z plus our change in heat flow in our z direction over our change in z at dz when it equals z multiplied by our change in the z direction minus z. And to simplify this down, we cancel those two out, that's going to be 0. We get our change in our heat flow in the z direction over our change in the z direction multiplied by our change in the z direction is our net heat flow in the z direction. And that's going to be the exact same format for both the radius and theta. So we have our heat flow, the radius, and change in radius, and the change in radius once again. And then for our theta, so our heat flow of our theta over our change in theta multiplied by theta. Plugging that into our conservation of energy equation, we get that our energy accumulation, our density multiplied by our heat capacity over our change in time is multiplied by our volume, of course, is equivalent to our change in heat flow over our change in z multiplied by our change in z, our heat flow of our radius multiplied by our radius, our heat flow of our theta, and our change in theta plus our energy generation, which is our heat flow multiplied by that volume. And from here, you want to simplify this down. What we can do is we can use Fourier's law and use the concept that our heat flow is equivalent to our thermal conductivity multiplied by an area multiplied by the change in temperature over a change in distance. We'll say it's z for this one. And that area, we're going to say, is equivalent to the radius multiplied by whatever unit we haven't used yet. So our theta and our radius, once again, multiplied by our change in temperature over our change in z for the z direction. And then our heat flow for our radius is essentially the same multiplied by our radius. We have our d theta, our dz direction, our change in temperature over our change in radius. Our theta is going to be a little different, and the reason is that you have to consider that theta you have to convert into the correct units. So you're actually going to divide by your radius and your change in theta. Now, because your heat flow is negative, your energy flowing out is negative, you want to remember that all of our net heat flows are negative. So plugging these equations that we just solved using Fourier's law into our net heat flow equations, and then plugging that right back in to our main equation, we find that density, heat capacity, temperature, and the change in temperature multiplied by the volume is equivalent to a very large equation that we can simplify down. That's the whole reason of doing this. And that's going to be our negative signs are going to cancel out from the thermal conductivity and the negative sign in front of our net heat flow equation. So it's going to be positive over dz, we'll start with dz, multiplied by heat flow for change in the z direction, which is our thermal conductivity, our radius, other radius, change in temperature in z direction, plus our r direction, thermal conductivity, our radius, change in temperature over our change in our radius, And that's going to be all multiplied by dr. This is going to be multiplied by dz. Oopsies. Can't forget that. That's very important. And then for our theta, you have our change in theta, our thermal conductivity multiplied by our change in z direction and change in r direction, change in temperature over our radius multiplied by our change in theta. Very important that you remember that. Multiplied by our change in theta plus our heat flow and our radius, or our volume. Now, what you can do with this equation is you can actually cancel out the volumes. So that volume can be canceled out, this volume can be canceled out, this volume can be canceled out, and that volume can be canceled out because it's present in every single element of this equation. And so if we simplify this even further, we can, we'll put that there just for sake of later. So multiplied by our radius, that's going to be equivalent to our derivative change in z direction, and we can remove our radius because there's nothing to derive it. So we're going to do multiplied by r, our thermal conductivity, multiplied by our change in temperature over our change in z direction. That's going to be added with our derivative of our change in r, multiplied by our thermal conductivity. Now, in this case, you can't take out r because it's gonna have a derivative since we have this little number right here. And then we're also going to add our change in theta. Once again, you cannot take the radius out of this equation either because you need it in order to transform our change in theta to a number that is able to connect with the other numbers. Otherwise, it will be in the incorrect units. Plus our heat flow multiplied by our radius. So let's take derivatives and cancel out our radius. Radii, cancel out our radii. From here, we'll do a couple things. The first one is dividing our density and our heat capacity over, removing our thermal conductivity from each of these equations, and that will get us the thermal diffusivity. So if we divide the density and heat capacity over, we get the thermal diffusivity multiplied by the net heat flow, yeah, for each dimension. So we also want to divide this radius over. That's a very important thing to do because we want to single out this part of the expression, our change in time over our change in temperature over our change in time, because that will let us know the heat diffusion equation for a cylinder. So we have change in temperature over our change in time, and that's going to be equivalent to our thermal diffusivity multiplied by our change in the z direction. Our r is going to cancel out, and that's going to be multiplied by change in temperature over the change in our z direction, plus 1 over r, our change in r, multiplied by r, multiplied by our change in temperature over our change in r, plus 1 over r squared. We can actually take this out and divide it by that r in the final right here, the final solution right there. Get our change in theta multiplied by our change in time over our change in theta plus our heat flow over our density and our heat capacity. And now the final part of deriving this equation is to combine all the variables. So we have our heat diffusivity is equivalent to our thermal diffusivity multiplied by the second derivative of our temperature over the second derivative of our change in the z direction, plus 1 over our radius multiplied by our derivative of our radius multiplied by our radius, multiplied by the change in the temperature over the change in our radius, plus 1 over our radius squared, multiplied by the second derivative of temperature over the second derivative of our change in theta. And last but not least, add our heat flow and divide that by our density and our heat capacity. So there you go. We've just derived a heat diffusion equation for a cylindrical coordinate. And we did that by using our conservation of energy, applying Taylor series expansion, as well as general knowledge of how to obtain a volume for a cylinder, and then put that together and simplified it down using Fourier's law to find this final equation. Use this equation that we just derived for our heat diffusion for a cylinder, and assume that there's no energy generated as well as the heat flow being radial, and that can give us the thermal resistance that's analogous for an electrical circuit. So let's take the equation that we just determined, and let's copy that over and use it in order to find that analogy between electrical circuits. So the first thing that you want to realize is that there's going to be no energy generated. So that cancels out this term as well as our accumulation. If heat flow is only in the radial direction, then we also know that we can cancel out our terms involving our theta and our z direction. So we have an equation where 0 is equivalent to our thermal diffusivity multiplied by 1 over our radius squared. No, sorry. Yeah, 1 over our radius multiplied by our change in our radius, multiplied by our radius, multiplied by the change in temperature over our change in our radius. That's a mouthful. From there, we want to integrate. Before we integrate, we can also divide both sides by our thermal diffusivity and multiply both sides by our radius to get a more simple equation. And now we integrate. So let's say that our radius multiplied by our change in temperature over our change in our radius is equivalent to c, constant c. Divide each side by our radius and then integrate from both sides. So our radius at 0 to our radius at our final f. And then our radius or our temperature at 0 to our temperature at the final. That's going to get us Tf minus T0. And that's equivalent to our constant times our final minus our constant times our initial. We can change this to be our constant multiplied by natural log of our radius f over our radius O. Now multiplying or dividing each side by that natural log RF over RO, we get C, our constant, is equal to our temperature final minus our temperature outer over our natural log identity. Now we're trying to find the temperature at the actual point in which we want to know the temperature. So we'll integrate once more, and we'll find that temperature of our starting position to the temperature that we actually want versus just the final temperature. It's equal to, it's the same identity, just replacing these variables with simply the radius or the temperature that you want to find. So our radius, our initial radius, and our constant divided by our radius. Integrate that, you get T minus T initial is equivalent to C natural log of your R minus your C natural log of your R initial. Simplify that down. You have your C natural log of your R over R initial. And we know that C is equivalent to this expression. Plugging that in, we get T final minus T initial over natural log of R final over R initial multiplied by our natural log multiplied by the radius we want to find divided by the initial radius. Next step is you're going to subtract your T initial over and get this expression, which we are going to take the derivative of in order to plug it eventually into Fourier's law. So we add our T initial. So we're taking the derivative of this expression, which means the change in T over the change in the radius is equivalent. And now, like before, this is C. So we're going to change that back to C in order to make this equation more easy to digest. So we'll have C, the derivative of C natural log, which is going to a natural log of R over R initial, which is going to be our initial over R multiplied by 1 over R initial, and this is just going to become 0. Let's plug back C to get this final equation. And then we will relate this expression to an electrical circuit. So the change in voltage is equivalent to our current multiplied by our resistance. How are we going to equate that to what we've just solved for? Good question. Well, we want to look at Fourier's law. And Fourier's law says that the heat flow is equivalent to negative thermal conductivity multiplied by the area multiplied by the change in temperature over the change in a distance. We'll say it's R in this case, the radius. So our area is going to be an area of a circle, which is 2 pi r. So our heat flow is going to be negative thermal conductivity multiplied by our area. And as you see here, this little expression is right here. And we can plug what we just derived into Fourier's law to get that our change in temperature divided by natural log of our final and our initial radius multiplied by our initial radius over the radius we are looking at. And there you go, you have your Fourier's law, which we're going to equate to our voltage. Now we can cancel out a few terms. So these two radii will cancel, and these two radii will cancel. Those are the radii we want to find and the radii that are initial, to give us a final equation to equate to our electrical circuit. But how does this relate to an electrical circuit? Well, we see a change in temperature. That's going to be delta T, and that is analogous to our change in our voltage. And our heat flow is analogous to our current. But what is the resistance? Well, let's switch around the equation to determine what that resistance is. So if we divide over and multiply over all of the expression that we don't want near our change in temperature, we get that our change in temperature is equal to our heat flow multiplied by our natural log, our final radius over our initial radius, divided by negative thermal conductivity multiplied by 2 pi. So our change in voltage is equal to our current multiplied by our resistance. Our voltage is analogous to our temperature, our current is analogous to our heat flow, and our resistance is analogous to this entire expression. Now, if you've been very observant through this entire process, you'll actually notice that I did not add a variable that is important to this equation. What variable is that? Well, we have our area, right, which we said is 2 pi r of a sphere, which is correct. You have your radius of your sphere and you multiply it by 2 pi in order to get that area. But a cylinder also has a height. And so you want to multiply your area by that height in order to get the complete volume. I always assume that the height is equivalent to 1, so I never add it into my equations, but it is still part of the process. So our complete analogy is our change in voltage is equivalent to our change in temperature, our current is equivalent to our heat flow, and our resistance is equivalent to our natural log of the initial and the final radii divided by negative thermal conductivity multiplied by 2 pi height of the cylinder.